faster. So we're going to skip the bonus because we don't have time, and it's pretty, if you want to, it's pretty straightforward. But the first question, we're given an array of the size of n, which contains a maximum heap, right? A heap we learned is stored in an array, but we don't know the size of our heap, right? The x first cells of the array are the actual heap, and the rest of them are just nothing. They just hold infinity because there's no elements in them. So basically, we have an array with n elements, but only the first x elements have. We have an array, size of n, but only the first x elements are actually, they have values, right? 1, 3, 5, 7, whatever it is. But then it just becomes infinities. And they're asking us, x is not, we don't know x. So we have to decide, we have to find the value of x where it stops becoming a heap and starts becoming infinity in logarithmic time of x. So O of log x, not log n, log x.
I think you did a mean thing, but it doesn't matter.
Oh, yeah, whatever. Okay, so we have
753.
yeah, whatever it is. This is our min heap, and then we have infinity. So we have to find the place that it stops becoming a min heap. Basically, the size of our min heap. But we have to do it in a logarithmic time of x and not logarithmic time of n, because n could be huge, and we don't want. Let's say if n equals 2 to the power of 100, but x is only 30, then we want it to be log of 30 and not log of 2 to the power of 100. Okay. So you can't do like a binary search. The binary search is log of the whole thing of n.
Okay, so should we answer or should we give them to think?
So I'll answer.
I was going to say you use the
just one word.
Exponential.
Exponential search. Exactly. We're just going to check every 2 to the power of I. Once we get to infinity, we know it's the range, right? And you basically need to prove, not prove, you need to show that this range is O of x. But like we did in the recitation in all exponential searches, there was like literally like 2 lines where you prove that it's O of x. And then once it's O of x, we can do a binary search on that.
Okay.
And a binary search is O of log x. So the first step is exponential search, which is log x, plus our binary search, which is also O of log x, and we'll find our smallest element. You have to change them a little bit and explain how that will work. Let's say the exponential search is just once we get to infinity, we stop. The binary search, you start in the middle. If it's a number, you go to the upper half. If it's infinity, you go to the lower half of the array. Okay.
Different, but no, because we know how a heap is built, so we go to if you know that the right element is 2i, so you keep doing 2i. So in the end, it's the same, but you know.
I got it. You just were going. It's the same thing. Just it's going multiplying by 2. But just this way, it's easier to like remember what you do. You do exponential search, and then you do what you're explaining of just going that way is the same thing as exponential search. Or maybe not, because it would be log of x. No, I think that will work too. It will work too.
Yeah.
Okay. Second question, and then we'll finish for today. Given a min heap that every level, all elements are the same. So let's say for this example, the first level has 1 element and it's equal 1. Second element has 2 elements and they're the same. The third level has 4 elements and they're all the same. So on and so forth. And this is the final level, right? Heap has, it's an almost perfect tree, right?
Yeah. This one just has 3 levels and then 4.
Exactly.
4 levels.
This is what this is what our example would be. Here there's 1, and then we have 2 and 2. Then we have 5, 5, and 5, and 5, and then we have 7, 7, 7, and 7. So what are they asking? We have to write a pseudocode algorithm that gets as an input one of these heaps and also another number z, and returns the index of some sort of element of z. Okay? So basically, if I give you
the zth element,
not the zth element, an element that equals z. So if I give you z equals 5, then z equals 5, then you have to just give me one of these elements.
so shouldn't we just like go left.
Yeah.
Exactly, but pay attention that
That
the runtime has to be to give you a specific runtime. O of log n. Okay? N is the number of elements in that heap. So you're right, Sam. You can just ignore all of these, right? That's a really good observation. You just ignore all these. This whole thing we don't care about. We only care about this part.
But is that log n?
But how many elements do we have here?
log n.
Log n. Exactly. So we have this size, the height of the tree is log n. Right?
So you need to do binary search on that part.
If you do binary search on log n elements, what's the runtime?
Log n.
Log n, because binary search is log the amount of elements. The amount of elements is log n.
You can't
The log
do binary search on
log.
the problem here is the
So how do you do binary search? Here we go. And then we'll finish with that. So binary search, you start with the middle, right? How many levels do we have? We have log n, right? We want to, if we start from here, how do we get to the next element?
2i.
2 times that same thing, right? So if we start at level 1, then the second element will be in the index 2 of the array. That's how we traverse the heap, because it's not saved like a tree, it's saved like an array. Okay, so it's just enough to traverse the heap. It's just doing arithmetic operations. So if we want to traverse this whole thing, it's just 2 times whatever we're at. So if we want to get to the middle level and compare our element to the middle level, how can we do that?
2 to the log n over 2. No.
2 to the power. But it's not, you don't want 2 to the power of log n, because that would get log n minus 1. Wait, log n round. What's this element? 2 to the power of log n rounded down. Right?
Yes.
If we have any more here, it'll round it down.
Sure.
If let's say there are 4 levels here, technically log n is 4 point something. We want to round it down to get to 2 to the power of 4. Right, so, but minus 1, because the first one is just 2 to the power of 0. Okay, so if we want to access this element, it's 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, which is basically the n element is 2 to the power of log n rounded down minus 1. Now that we have this, how do we get to the middle element?
We do the first one and plus the last one divided by 2.
You can do it that way, yeah. Or you could take this and divide it.
No, I mean, because you have to write pseudocode, then.
Exactly. If that's the right pseudocode, then you should do it with the n. Where you take the first element and the last element. So this would be the first element, and this would be the last element, which is the log n. You add these two together, divided by 2, and you get the middle element. So technically we did it, like the idea of it, we just talked about, and you guys understand the solution. Technically though, they're asking for pseudocode. So you'd have to write all that we said verbally, you'd have to write it in a pseudocode algorithm, which basically starts with, how does binary search work? You start with low and a high, like a bottom bound and an upper bound. And then basically you take the middle, this one plus this one, divided by 2, you take the middle. You compare your element to the middle. If it's greater, we can recursively call on the smaller half. If our element z is smaller than our thing, then we know we have to go to the bigger half, to the larger half. That's how binary search works, right? If we have just an array, binary search, we just look at the middle element.
We have to go to the top half.
If it's smaller, we have to go to the larger half, the top half. So it's the same thing here, we have to go to the top half. But here it's just a little bit more complicated. Once you understand the trick, just a little bit more complicated than regular binary search because you have to understand how to traverse the heap. That this is just times 2, times 2, times 2, so 2 to the power of whatever level you want to go to. So if we have log n levels, you do log n rounded down, log n, plus this one divided by 2. And that's how you do it in pseudocode. Okay, but idea-wise, you could technically just this divided by 2, right? Because this is the highest one. The first one is just that divided by 2. Okay, any questions on this, where you just take the minimum, the maximum, add them both, take the average of them, which will give you the middle one, compare it to your element, and then recursively call on either the lower half or the upper half. And you just recursively call like binary search, classic divide and conquer algorithm. Any questions?
Well, this.
What?
I've got a question about that one.
Okay, all right.
Thank you so much.
So I'll
I'm
see you guys
sorry.
next week. It's the last time that I'll say see you next week, but
Now you can be our practitioner.